nodes in tree. You may hear me use the word fully qualified domain, and that is the whole name, such as www.icann.org. Labels are very important because they represent what's called a delegation. Each time someone goes and registers a domain name under a top-level domain, they actually become responsible for running this part of the domain name system. So, for example, at ICANN, we are icann.org. The org top-level domain is not run by ICANN, but the ICANN second domain is run by ICANN. And these establish administrative boundaries. There are many operational components to help us operate and manage and distribute the burden of dealing with billions of names that are resolved on a daily basis now. At the very top of this hierarchy of operational elements, we have what are called authoritative name servers. These are the name servers that actually publish the associations between names and addresses. So if you were to go to icann.org, we would have www.icann.org published and the address of www.icann.org also published in what we call a zone file. And if you go to any domain within the .ec top-level domain, you would see the same thing. So this is where the answers are. You think of the authoritative name services where the answers are. Okay. The recursive names are where we go to ask questions. If those of you who are old enough to remember when we had directory assistants in the telephone number, these are the directory assistance operators. So everyone goes and asks what are called resolvers questions, and then the resolvers provide answers. There's a special kind of resolver that I'll talk about in a little later called a caching resolver. But all the devices that we use, our mobile phones, our tablets, our laptops, even the servers that host Amazon.com, eBay, and the like, all have what are called stub resolvers. The stub resolvers ask the questions. So stub resolvers ask questions to recursives. Recursives ask questions to authoritatives, and authoritatives give answers. So let me show you quickly how this works in real life. On my PC at ICANN, if I want to go to www.icann.org, I would ask, what is the IPv6 address for www.icann.org? So the stub resolver here actually asks the question to what's called a local resolver. The local resolver doesn't actually take any action at this point. He's going to now go out on the internet and ask authoritative resolvers questions, and they will give him answers. So that resolver will first go to the root, because that's where he goes when he doesn't know anything else but the root name server. And he'll say, do you know the address of www.icann.org? And the root, of course, doesn't know this because it is a distributed system. So the root will say, I don't know this, but I can tell you what the name servers of the top-level domain org are, so you can ask them. Now the recursive does the same thing. The recursive resolver goes and asks a name server that operates the org zone, what's the IP address of icann.org? He doesn't know that either. What he knows is the name server address for icann.org. So he'll return the name server address to that resolver, and then the resolver has one more question to ask, and he says, can you tell me what the address of www.icann.org is? And of course, this is where ICANN hosts its name zone file, and this is where he'll get his answer. So the answer is here, and then that's sent back to the recursive resolver, and the recursive resolver sends it back to my client. This happens typically in somewhere between 40 milliseconds and 280 milliseconds all over the globe. It's a rather remarkable, resilient system. I mentioned caching earlier. One of the things that resolvers can do that is very, very important in improving performance is they can peek at answers. Okay, so when I ask a question, what is the IP address of www.icann.org, and I've asked it through my local resolver, I'd ask the ICANN server, he'd return it, and the local resolver will dutifully return it back to my PC, but he's also going to grab a copy. okay? And he's going to store it locally so that next time someone asks for that, that answer will be local. But you can see that this is a very, very important service on the internet. And because it's a very, very important service, it is also a very, very opportunistic target for abuse and misuse by criminals, by terrorists, by hacktivists. And there are many, many different motives, to attacking or exploiting the DNS. I spend most of my time working in cybercrime, but as the gentleman from Kaspersky illustrated, looking at DNS requests is also a very good way to identify malware, to protect a corporation or a government network. Okay, there are also ways in which civilian attacks on other civilians and terrorists can actually be can be monitored using DNS requests. One of the things that that I've done when I've trained law enforcement in different countries is we talk about how to find terrorist radicalization and recruitment sites. And so the DNS is used very much by those people. Each of those components that I pointed to earlier has a different kind of attack that can be leveraged against it. Some of the attacks try to deplete bandwidth. They try to exhaust the access pipe of the name server or of the resolver. Some of them try to do the same at network elements, compromising them or disrupting them for service. And the attacks can be at various levels. They can be either attacks on the name server software or the operating system software or the hardware itself. We can actually see, and I'll show you an example of how someone can alter the contents of a cache. And then there's other kinds of attacks that have to do with administration and configuration that hopefully we'll have time for. The attacks, am I going fast, too fast for the translator, or is this okay? The kinds of attacks that we're going to look at fall into a number of different categories. And some of these attacks have been around years and years. The first we'll look at is an exploit to fail. Then we'll look at exploit to own. And then a number of different kinds of attacks that are typically seen in denial of service. And then we'll look at a cache poisoning attack and an exhaustion attack. So an exploit to fail attack has one purpose. The purpose is to cause the name server to actually stop operating. So that would disrupt service. You can imagine that this would be very attractive for someone who wanted to take down a government site. Okay, so if they could find an exploitable bug in the name server software, for example, on the name server that's hosting a government site or hosting Amazon or whatever, then if the attacker wanted to disrupt service, what he would do is he would send what's called a malformed DNS message. So this is a query that, for some reason, possibly a bug in the name server can't process, and because it can't process it, it actually stops running. Okay, so this is called exploit to fail. And what happens is the name server just simply, the software in the name server stops. Okay, those of you who have had Windows machines in the past and have seen blue screen of death, this is similar to a blue screen of death for a name server. by flooding memory that's being reserved for caching it. One of the ways to flood memory is to send a non-existent domain, send a query that will evoke a non-existent domain, or the domain is not registered response, because those kinds of queries are actually put into the cache. And if you do this constantly through a local resolver, again, you would deploy the memory that, that the caching server has allocated for cache, and then he wouldn't be able to put any more new entries in until the times to live of all these expire. We've talked about attacking the infrastructures, the top-level domain or authoritative name servers, the second-level label authoritative name servers, and the resolvers. There are also a number of attacks that can be perpetrated against all your devices. So this gets rather depressing, doesn't it? It's like I'm only halfway through the through the presentation, and we're at a point where we tend to try to give up. But this afternoon I'm going to talk to you about ways that we can fight back. So the first kind of attack is simply called is simply one variant of a man-in-the-middle attack, where the attacker tries to interpose himself between the client and the server, or the client and the resolver. Okay, and so there are a number of ways that you can do this, and many broadband access routers these days actually have problems with compromised access points or access routers. There's also a way to do what's called ARP poisoning, which changes the address that a client understands to be the local resolver's IP address. Or how many have ever heard of what's called an evil twin access point, a wireless access point? So an evil twin wireless access point is an attacker's computer, and what the attacker does is he actually uses significantly more power and amplifies his radio signal, and uses the same SSID as a legitimate site like an internet kiosk, or even here, like he would use the SSID CyberRec, and by using more power, all the devices will actually try to associate with the strongest signal. So they'll actually go to the evil twin, which is a Star Trek allusion to the evil Kirk, right? And then the attacker has someone in the middle. And so once you're in the middle, you go up through the access point, and the attacker's resolver now sends back a fake website address, and now when the for the DNS response to the bank, and now my PC thinks he's getting the right address to get to my bank, but instead he's taking a redirected path over to a fake bank website. Okay. Unfortunately, there's a growing market for helping people solve errors. And solving errors in the domain name system can have some negative consequences. So one of the things that it has been a target for what's called monetization, getting money out of logging or other information, or redirection, is that certain ISPs will partner with an organization. There's one called Bear Fruit, and what they will do is when a client contacts their resolver, and the resolver goes out and it asks for a question and there's no answer, says that domain doesn't exist, instead of sending back that domain doesn't exist message, they actually send back what's called a modified response. They'll send back the IP address of a page that they're hosting that has ads or for revenue, or has a custom search engine. And there are some people who do this with the idea of making money. There are some people who do this with the idea of hijacking or redirecting traffic. But the result is that instead of finding out that a host I'm trying to connect to, for example, if I mistype www.icann.org and instead I go to www.icann.org, you would now get back a response instead of finding out that you mistyped. And the response would take you somewhere else. And there's a gentleman by the name of Dan Kaminsky who's done some very, very interesting work on how these kinds of attacks can compromise entire web.